Welcome to my fourth video about how to alkylate carbon nucleophiles. This presentation is about the alpha alkylation of aldehydes. Aldehydes are usually more acidic than ketones and their enolates therefore less basic and less nucleophilic. Nevertheless, a number of strategies have been developed that enable high-yielding aldehyde alkylations. Like ketone enolates, aldehyde enolates are ambident nucleophiles that can react with electrophiles either at carbon or at oxygen. Weaker bases than those required for ketones can already be sufficient to bring about enolate alkylation. Also, if neutral aldehydes are alkylated by strong carbocation-like electrophiles under acidic conditions, both carbon or oxygen alkylation can occur. Because of their high electrophilicity, incomplete enolate formation often causes aldehydes to undergo aldol addition much more readily than ketones. But even if aldehydes are deprotonated stoichiometrically, upon C-alkylation a free aldehyde is formed which can react with the aldehyde enolate. Despite these problems though, aldehydes can be alpha-alkylated, and I'll show you some examples in a minute. Aldehydes are more acidic than ketones and their enolates therefore less basic and nucleophilic. Some aldehyde enolates may therefore only react slowly with a given electrophile, and aldol reactions of the product may compete effectively with the alkylation reaction. In such instances, complex product mixtures will result. This is for instance the case when the lithium enolate of acetaldehyde, which is accessible by butyllithium-induced fragmentation of THF, is treated with alkyl halides. In an article from 1977, the authors reported that despite several attempts, no alkylation products, but only polymers were obtained when treating the lithium enolate of acetaldehyde with reactive alkyl halides. Therefore, indirect strategies for the alpha-alkylation of aldehydes are more relevant than for ketones. If the target aldehyde does not contain sulfur, olefins or alkynes, the best alternative to alkylation is aldol condensation followed by hydrogenation. These reactions do not require strong bases, low temperature, expensive catalysts or photochemical equipment, and can sometimes be conducted without any solvent. Aldehydes are not readily hydrogenated under the standard conditions of olefin hydrogenation, and no primary alcohols will usually be formed. A second alternative is the deprotonation and alkylation of aldehyde-derived imines or hydrozones. These are less electrophilic and acidic than aldehydes, and therefore easier to alkylate without simultaneous self-condensation. Further indirect strategies include the alkylation of aldehyde-derived enamines or silyl enol ethers. I'll discuss the alkylation of enamines more thoroughly in a later video, but in general, enamines only react with strong alkylating reagents, such as benzylic or allylic halides, haloacetic acid derivatives, and alpha-haloketones. Silyl enol ethers usually require acidic reaction conditions and carbocation-like electrophiles to undergo alkylation. The main advantage of the direct alkylation of aldehydes is the ready availability of the starting materials. As discussed in earlier presentations, aldehydes can be obtained by oxidation of primary alcohols, and suitable alkylating reagents such as alkyl halides or sulfonates can also be prepared from alcohols. Main disadvantages include the low reactivity of aldehyde enolates and the fact that aldol additions of the starting or alkylated aldehyde proceed at high rates. Moreover, aldehydes readily undergo a large number of side reactions, such as disproportionation or oxidation, in particular in the presence of nucleophiles or strong bases. This is an example of successful alpha-methylation of a structurally complex polycyclic aldehyde. A large excess of base and methyl iodide were used to attain a high conversion and yield. Methyl iodide is particularly well suited for methylations at carbon because of its high polarizability. No methylation at oxygen was observed in this instance. Also, linear aldehydes can be alkylated. In this highly optimized example, propanal was benzylated in a biphasic solvent mixture with sodium hydroxide as base and with the aid of a phase transfer catalyst. The desired product, a fragrance called Lilial or Lysmeral, was obtained in high yield without the need of a large excess of base or propanal. The electrophile in this example was the allylic quaternary ammonium salt formed from an allyl bromide and DAPCO. However, because the olefin was activated by an electron withdrawing group, I would rather classify this reaction as an enantioselective Michael addition followed by elimination of DAPCO. Aldehydes undergo Michael additions readily, and it is often difficult to prevent multiple alkylations if these are possible, as in the example on this slide. For this reason, a large excess of aldehyde was used, which probably also underwent dimerization by aldol addition. This is an example of one of the indirect strategies mentioned earlier. The starting aldehyde was first condensed with cyclohexylamine and the crude imine deprotonated stoichiometrically by treatment with LDA. After alkylation with an alkyl bromide at low temperature and hydrolysis, the alkylated aldehyde was obtained. Alcohols which readily form carbocations, such as benzylic or allylic alcohols, can sometimes be used directly to alkylate aldehydes. In this example, isobutyraldehyde was allylated in high yield just by heating with allyl alcohol and catalytic amounts of toluene sulfonic acid. A high boiling dialkyl arene was used as solvent, and potential side reactions were the allylation of the arene or hydride abstraction from the benzylic position of the isopropyl group. None of these occurred, however. This is a further example of alkylation with an allylic alcohol. In the presence of an iridium complex and chiral ligands, the allylation proceeded with high enantioselectivity. Aldehydes readily enolyze, however, and are therefore configurationally labile and should be quickly converted into a more stable product to prevent racemization. So, what can go wrong? Unfortunately, many things. Because aldehyde enolates are ambident nucleophiles, alkylations can occur both at carbon and at oxygen. In this example, the electrophile was an alpha-chloroether. These are hard, cation-like alkylating reagents with a high tendency to alkylate hard nucleophiles. In fact, almost 30% of O-alkylated enolate resulted in this reaction. The first example I showed you was a methylation with methyl iodide and potassium terzbutoxide as base of a similar starting aldehyde. In this case, no O-alkylation was observed. A further alternative could be to treat the aldehyde first with formaldehyde and a base and then benzylate the resulting alcohol. Benzylic amines in ethers are readily oxidized by oxygen to benzylic peroxides or alcohols, which in turn readily form stabilized carbocations. These carbocations, like iminium salts, react with the enol form of aldehydes to yield alpha-benzylated aldehydes, as in this example. Thus, in the presence of such benzylic ethers or amines and air, unintended benzylations of aldehydes may occur. Further potential side reactions include Mannich reactions, that is, the alkylation of aldehydes by iminium salts, and aldol additions and condensations. Then, in the presence of light, enamines or enols can form allylic radicals and cause the formation of beta-alkylated aldehydes. Strong bases, such as alkali hydrides or deprotonated secondary amines, can also act as hydride donors and occasionally reduce aldehydes instead of deprotonating them. Moreover, aldehydes readily disproportionate, for instance in the Cannizzaro or Tichenko reactions. In the presence of acids, aldehydes may also act as electrophiles and hydroxyalkylate electron-rich arenes or olefins, as in the Prince reaction. Finally, strong nucleophiles can bring about the dimerization of aldehydes, as for instance in the benzoene condensation. On this and the next slide is a selection of further references. Unfortunately, many of the newer examples require both expensive noble metal catalysts and photochemical equipment and can therefore not be readily scaled up. Sometimes I get the impression that in academia there's a race to develop the most unrealistic procedures conceivable. In fact, I once had to review an article about a photolytic procedure at -78 degrees in the presence of large amounts of a noble metal catalyst. Well, it is unlikely that such procedures will ever attain any practical relevance, but perhaps they may serve to discover new reaction mechanisms. The next video will be about the electrophilic alkylation of ester enolates. This works much better than the alkylation of aldehydes and is a valuable method for the preparation of branched and even enantiomerically enriched carboxylic acid derivatives. So, don't miss it.